Hello everyone. So in this session we are going to discuss important concepts and some important questions from the subject electric drives, TSPSC EEE Polytechnic Lecturer post, right? Yeah. So first the syllabus of the course. Here the 4-quadrant operation of a drive, right? 4-quadrant we know: forward motoring, forward braking, reverse motoring and reverse braking operation. Next, types of the loads: active load, passive load, etc. Energy loss during starting and braking of DC and AC motors. Types of braking in DC and AC motors, right? Rheostatic, plugging and regenerative braking. Basic concepts of converter and chopper fed DC drives. This point is important. Basic concepts of converter and chopper fed DC drives. You can refer the previous question papers, right? Some simple questions they have asked, and as long as the drive questions are considered, you need to only recall the output voltage expression of the specific converter. In the numerical they will give you the converter type, okay? So you require the output voltage expression of the converter and some basics of the electric motors. That's it. Next, variable voltage, variable frequency control, that is inverter fed drive. Static rotor resistance control, slip power recovery scheme of 3-phase induction motor drives. Okay. So if you recall or if you refer the previous year question papers, hardly you will get 2 to 3 questions. And sometimes they ask the theory questions, right, based on the braking of the motor. Sometimes they ask the questions like some numerical type of the questions, okay, right. 2 to 3 questions you can expect on this subject, okay, right. So let us discuss some important concepts from the subject electric drives. So fundamentals of electric drive. So my dear friend, drive means a motion control. Drive is a general term. It is not only related to the electrical engineering, okay. So drive is a general term. Drive means a motion control, and in a drive system, if electric motor is used, then it is known as electric drive, right. And as long as the electric drive is considered, motion control is nothing but a speed control, right. Motion control means only speed control, right. So what is the ultimate motto of this course? The ultimate motto is to control the speed of the motor, but using the power electronic converters, right. So power electronic converter used for speed control of the motor is nothing but your drive system, all right. Yeah, yes. Motion control is required in large number of industrial as well as domestic applications, like your transportation systems, your paper machines, fans, etc. Okay, you can find large number of examples, okay. Next, where the speed control is required. Next, system employed for motion control are called drives, and the drive system which uses electric motor are called as electric drive, right. Yeah. So the block diagram of electric drive, this is a simple block diagram of electric drive system. Here we are having the various blocks. First one is the source, right. The source can be AC or DC. It depends on the location where you are designing the drive system or where you are installing the drive system, right. In India, easily available supply, we know it is a AC, right. Yeah. So source, it can be AC or DC. Next, here we are having the load. So based on the requirement of the load, you need to select the particular motor, right. The motor which fulfill the requirement of the load, that particular motor we need to put here, all right. For example, suppose for a particular application we are interested in controlling the speed of a motor from 1000 rpm to the 1500 rpm, between 1000 and 1500. And let us consider the suitable motor for this load, particular load, is a DC motor. I am saying here the motor we are using, suppose a DC motor. And as we know, in India easily available supply is a AC. So suppose at a particular location we are designing the drive system, and at that particular location the available supply is a AC, but my suitable motor to fulfill the requirement of the load is a DC. Can I directly feed this AC supply to the DC motor? No. So for that, here we need to take the help of power electronic converter, that is nothing but the power modulator. Power modulator will take the source input, that is AC, and it will convert in as a output so that it will be suitable for your motor, right? So here if input supply is AC, available supply is AC, and if motor is suitable is a DC, then here power modulator is nothing but your rectifier. Here we need to use the rectifier, right? So my rectifier will convert AC to DC, and now that DC I can feed to the DC motor directly, right? As I said, we are interested in controlling the speed of the motor. How to vary the speed of electric motor? So in order to vary the speed of electric motor, simply we need to vary the input to the motor. We need to vary the input to the motor, right? So here this is my rectifier unit. This rectifier will convert fixed AC to the variable DC. So here I am getting the output as a variable DC, right? Now output of the rectifier is controlled by your control unit. And how the control unit is generating the control signal? The control unit will generate the control signal based on actual output and reference input. Here you will be having the actual output and here a reference input. Right? Yes, here we are using the sensing unit. The sensing unit will sense the actual output of the motor, and it will give that actual output as an input to the control unit, right? Control unit will compare the actual output and reference input, and based on that the control unit will generate the controlling signal, and that controlling signal will control your power modulator. In this case particularly it is a rectifier, right? The type of the or the nature of the control signal or the output of the control unit, it depends on the nature of your power modulator. If your power modulator is a rectifier, then the output of the control unit will be in a form of firing pulses or a firing angle, you can say, right? Next, if your power modulator is a DC to DC converter, that is a chopper, then here your control unit output or control unit output or the control signal will be in a form of a duty cycle, in terms of a duty cycle. All right. So this is my simple block diagram of electric drive system. Next, types of electric drive. Yeah, we know in electric machines you might have studied the DC motors and AC motors, right? The speed control of DC motor using the power electronic converter is nothing but your DC drive, and similarly we are having the AC drive. Okay, so types of the electric drive, there are two types, DC drive and AC drive. In a DC drive, the DC motors are used. Generally for speed control the suitable motors are DC series motor and separately excited DC motor, right? DC series motor and separately excited DC motors are used. Now which converters, which power electronic converters we can use in a DC drive? Here DC drive means the speed control of DC motor. If I want to control the speed of DC motor, means I need to give the variable DC as an input to my DC motor, right? So variable DC, which converters gives the output as a variable DC? Recall the power electronics. Which converters gives the output as a variable DC? Chopper and rectifier, right? So here power electronic converters such as rectifier or choppers are used. Okay, right. Here always keep in mind, output of power modulator is nothing but input to the motor, right? Input to the motor. So in DC drive, chopper and rectifiers are used. Similarly, in AC drives, AC drive means is nothing but the speed control of AC motor. Which motors we can use? Yes, popularly the induction machines are used, and in some of the specific applications, synchronous machines are also preferred. Okay, and which converters we can use? The converters which can give the output in form of variable AC. So which converters gives the output in form of variable AC? We're having the inverter, right? So inverter gives the output in form of variable AC, and AC to AC converter, AC to AC converter. In AC to AC, we are having AC voltage regulator, AC voltage regulator, and cyclo converter, AC voltage regulator, or it is also known as a AC voltage controller. Okay, right. So these converters are used in AC drive, right? Next, classification of load torques. So there are two types. One is a active load torque and second one is a passive load torque. Active load torque means the load torque which have the potential to drive the motor under equilibrium condition, right? So active load torque is having the potential to drive the motor under equilibrium conditions, right? Similarly, passive load torques. Passive load torques is nothing but those are the torques which are only in opposition to that of the speed of the motor, speed direction. Okay, right. So load torques usually retain sign when the drive rotation is changed. Next, passive load torques. Load torques which always oppose the motion and change their sign on the reversal of the motor, right, are called the passive load torques. Torque due to friction comes under the passive load torques, right? Yeah. Next, let us have some discussion on basics of DC machines, right? Here I am not going to teach you the DC machine, okay? Only some important points we are going to focus here, okay? Right. You might have familiar with these expressions as well, okay? Right. So DC machines basics. So first thing is, we know back EMF, EB expression. Yes, it is phi P Zn upon 60 into A. Yes or no? Back EMF EB is equal to phi P Zn upon 60 into A, where phi is the flux per pole, P is the number of poles, Z number of conductors, N speed in RPM, 60 constant, A is the number of parallel paths. All right. So EB equal to phi P Zn upon 60 into A. Next, now motor speed or angular velocity of motor omega m is equal to 2 pi n by 60. So from this I can write n equal to 60 into omega m upon 2 pi. At the end of the discussion, we are going to get the two expressions. Those expressions are important. Okay, right. So n equal to 30 into omega m upon pi. Now let me put this n expression in this EB expression. Okay, right. So therefore I can write EB equal to phi P Z into 30 omega m upon pi upon 60A. Further, this can be written as phi P Z into phi P Z into omega m upon 2 pi E, right? Once the machine is constructed, then your number of poles, number of conductors, number of parallel paths will remain same. 2 pi is also constant. Okay, so here I am taking all the constants in one bracket. So it is Pz upon 2 pi A into phi into omega m, right? So EB, so I am writing this as EB equal to some constant k, let me write it as a k, into phi into omega m, where k equal to Pz upon 2 pi E. Yeah, this is simple expression. Now we know back EMF is proportional to flux into speed. Yes or no? Right? So here k is a proportionality constant, which is equal to Pz upon 2 pi E. Pz upon 2 pi E. Right? Next, so EB is k phi into omega m. Also, we know electrical equivalent of mechanical power developed by the motor and actual mechanical power output of the motor, both are equal, na? Right? Recall the expression. Electrical equivalent of mechanical power. Electrical equivalent of mechanical power developed by motor is equal to mechanical power output. Mechanical power output. Now what is electrical equivalent of mechanical power? Yes, it is EB into IA, right? Which is equal to mechanical power developed is equal to omega m into T, right? So from this I can write EB is k into phi into omega m. So it is k into phi into omega m into IA is equal to omega m into T, right? Omega m will get cancelled out. So therefore I can write T equal to k into phi into IA. This also we know, na? Torque is proportional to flux into armature current, right? Yeah. So T equal to k into phi into IA, right? So here k and here k both are same. This k is known as a motor constant, where k, sometimes in numerical they will give the motor constant, right? Some value. K is a motor constant. K is a motor constant, right? Next, so these are the expressions for general DC motor. This torque is equal to k into phi into IA and EB equal to k into phi into omega m, right? These two expressions are for general DC motor. These two are the important expressions, okay, right? We'll discuss how to solve the problems by using these expressions. Next, now we are going to modify these two expressions for DC series motor and separately excited DC motor, okay, right? So let us first discuss for separately excited DC motor, right? Yeah. So this is my separately excited DC motor equivalent circuit, right? EB, that is the back EMF of the motor, V0, or you can write it as a VA. V0 means output voltage of your converter, which is nothing but input to your motor, input to the motor, right? And here the field winding is excited using the external supply, right? So separately excited DC motor means excitation to the field winding is given using the separate source. So that's why it is separately excited DC motor, all right? Next, now here separately excited DC motor, we know the flux is a constant because this voltage source VF value will be constant. So my IF will be constant, right? So therefore my flux will be constant. So for separately excited DC motor, flux is a constant. Flux is a constant. Now for separately excited DC motor, if flux is constant, then what will the expression for EB? Recall here we have written EB equal to K into phi into omega m na, right? EB equal to K into phi into omega m. EB equal to K into phi into omega m. I am writing this as K into phi into omega m. K is a constant, phi is also constant now. So product of the two constants will be again constant na, right? So let me write it as is equal to K1 into omega m. So EB equal to K1 into omega m. We know na, in separately excited DC motor, back EMF is proportional to only speed, right? Because flux is a constant, right? Yeah. So where K1 equal to, where K1 equal to K into phi, K into phi, right? This K1 is known as a motor constant. K1 is known as a motor constant. Next, now what is the torque expression for general DC motor? T equal to K into phi into Ia, right? So I am writing it as T equal to K into phi into Ia. But K is constant, phi is also constant. So I am writing it as a K into phi in one bracket, both constants, right? So product of the two constant is constant. So it is equal to again K1 into Ia. So torque is equal to K1 into Ia, right? So from this, can we say that K1 is a motor constant and unit of motor constant is, check here, T equal to K1 into Ia, right? Unit of torque is Newton meter. Unit of Ia is ampere. So from this can I write K1 equal to T by Ia? If K1 equal to T by Ia, then what is the unit of K1? Newton meter per ampere, right? Where K1 is, it is equal to K into phi, is a motor constant. Motor constant. And its unit is Newton meter per ampere. Newton meter per ampere, right? So for separately excited DC motor, this expression and this expression, these two expressions are important. Sometimes they will give the motor constant value directly, okay? So we need to use the motor constant value, right, in these two expressions, and from that you can find the torque value, you can find the EB value, etc. Okay, right. Next, so this is about the separately excited DC motor. Now let us modify the expression of EB and torque, right? This is for general DC motor. This is also for general DC motor. Let us modify this EB expression and torque expression for DC series motor. DC series motor, right? So, yeah, DC series motor. We know in DC series motor, field winding and armature winding are connected in series, right? So RF, RA, these are connected in series. Now we know in DC series motor, flux phi is proportional to armature current. Na? Flux phi is proportional to the armature current, right? Now this can be written as flux phi is equal to, let me write some constant C into Ia, where C is a constant of proportionality, right? So phi is proportional to Ia, so phi is equal to C into Ia, I am writing, right? Now let us write the expression of back EMF EB. EB equal to K into phi into omega m, right? EB equal to K into phi into omega m. So this can be written as K into phi means C into Ia. So K into C into Ia into omega m. Further this can be written as K is constant, C is also constant, na? So I am taking these two constants in one bracket, K into C into Ia into omega m. Product of the two constants is a third constant, right? So let me write it as a K2 into Ia into omega m. So EB equal to motor constant K2, where K2 equal to K into C. K into C, right? EB equal to K2 into Ia into omega m, right? Back EMF expression. Next, torque. We know for general DC motor torque expression K into phi into Ia. Yes, T equal to K into phi into Ia. But what is phi? C into Ia. Into Ia. So this can be written as K into C into Ia square. But K into C means K2, that is motor constant, into Ia square. This is torque expression, right? Where K2 is motor constant. K2 is a motor constant, right? Motor constant. What is the unit of K2? Yes, Newton meter per ampere square. K2 means what? T by Ia square, na? Unit of torque is Newton meter and Ia square will be ampere square. So, in Newton meter per ampere square. Newton meter per ampere square, right? So, these two expressions, torque is equal to K2 into Ia square, EB equal to K2 into Ia into omega m. You can write K2, you can write K, doesn't matter because it is only constant, it is only constant, right? Yeah. And for separately excited DC motor, we are having the two expressions. So these four expressions are important, right? EB and for torque. 2 for DC series motor, 2 for separately excited DC motor, right? Next. Now classification of electric drives. First classification we discussed AC drive and DC drive. Those were the general based on the motor, okay? Right. Next, according to the mode of operation, you may get the theory question, okay, based on this information. According to the mode of operation, the electric drive are having three types: continuous duty drive, short time duty drive, and intermittent duty drive. Continuous duty drive means the drive system in which the load on the motor is put for the continuous time, right? Motor is continuously loaded. Here, short time duty drive means for short time only the motor will be loaded. For remaining period, it will be like in either in a off state or it will be like in a no load. And third is intermittent duty drives, right? Means it is a combination of the two, right? Yeah, variation of the loads. Next, according to means of control, manual control, semi-automatic and fully automatic, right? Straightforward. According to the number of machines, individual drive and group drive, right? Individual drive and a group drive. Next, introduction to 4 quadrant operation. Yes, so we are having the two modes, motoring and braking. In every mode, we are having the forward and the reverse, okay? Right. A motor operates in two modes, motoring and braking, right? In motoring, it converts electrical energy into mechanical energy. Motoring operation, electrical energy input, output is a mechanical energy which supports its motion. In motoring operation or motoring mode, always keep in mind the motor rotates due to torque developed by the motor, right? In a motoring operation, motor rotates due to torque developed by the motor. So in motoring operation, the torque direction and the speed direction both will be same, right? But whereas in a braking operation, motor speed and motor torque both will be in a opposite direction, Next, in braking it works as a generator, yes, works as a generator, converting mechanical energy into electrical energy and thus opposes the motion, Next, so there are 4 modes: forward motoring, forward braking, reverse motoring and reverse braking. You can check in forward motoring and reverse motoring, the torque and speed both are same direction, torque positive, speed positive. Here also torque negative, speed negative, third quadrant operation, right? So reverse motoring. Whereas in a braking operation, torque and speed will be in a opposite direction. Means it is like suppose you are having a motor which is running at some particular 1200 RPM in clockwise direction, right? Now we know when motor rotates at a particular speed, then the back EMF will be non-zero present, right? There will be the back EMF present which is having a non-zero value. Next, now if I want to put the brakes on the motor, means I am going to put the opposing torque, right? The torque which is opposing to the speed, that is nothing but the braking. So here speed positive, torque negative, so it is a braking operation. Here torque positive, speed negative, this is also braking operation, right? So in motoring operation, speed and torque both will be in the same direction. In braking operation, speed and torque both will be in the opposite direction. Next, so types of the electric braking, there are three types: dynamic or rheostatic braking, plugging or reverse voltage braking, and regenerative braking. So let us discuss one by one. Dynamic or rheostatic braking, right? In dynamic or rheostatic braking, first of all, the motor is disconnected from the supply and it is connected across the external resistor. It is connected across the external resistor. Yes, in this method of braking, the motor which is at a running condition is disconnected from the source and connected across a resistor. Connected across the resistor. This value of the resistor depends on your allowable braking current value. Allowable braking current value. Next, when the motor is disconnected from the source, the rotor keeps rotating due to inertia and it works as a self-excited generator. When the motor works as a generator, the flow of the current and torque both will be opposite. So here it is a circuit diagram. Separately excited DC motor. First thing is, when your motor is operating in a motoring mode, then how will be the circuit? For motoring mode, your circuit will be like this. For motoring mode, circuit will be like this. Yeah, this is a separately excited. So suppose the external supply is present here and here it is a EB. This is supply voltage, or you can write it as a VA. How is my IA direction? This type. This is your motoring operation, right? Flux is constant. Flux is a constant, right? IF is a constant. It is in a downward direction only, right? Now tell me here, IA is flowing in a clockwise direction, right? Armature current is flowing in a clockwise direction in this circuit, right? So it is EB. Now tell me, I applied some voltage here. My motor is rotating at a particular speed, non-zero speed. If motor speed is non-zero, then therefore my back EMF value will be also non-zero. Now if I disconnect this source and if I put a resistor like this, then tell me what will happen in the circuit. If I disconnect this and if I put the resistor here, then this back EMF will be acting as a source now. This EB will act as a source. This EB will act as a source. In this case, current direction was like this, right? And EB polarity plus here, minus here. When I disconnect this supply and when I put the resistor here, then this back EMF will act as a source and the current will flow like this, EB, this RB, and again back to the armature. Yes or no? Like this the current will flow. Now tell me, the armature current direction in this case is anti-clockwise direction. Na? Here armature current direction is anti-clockwise. Here armature current direction is clockwise. Field current direction in this case also downward, in this case also downward, right? So if my field current direction is same, means my flux direction will be same, right? So flux direction is same but armature current direction is reversed. Recall the torque expression. Torque is proportional to flux into armature current. Na? Torque is proportional to flux into armature current, right? So flux direction is constant now, same in both the cases, flux direction is constant, but armature current direction is reversed. So if armature current direction is reversed, so definitely your torque will be getting reversed, right? So here torque and in this case torque both are opposite, all right? Yes. So here motor is disconnected from the supply and the external resistor is connected across the motor terminals. This is simple. Separately excited DC motor, rheostatic braking. Similarly, for DC series motor, the connection diagram for rheostatic braking. Be careful. For DC series motor, during motoring operation, you will be having the circuit like this. DC series motor. This is your field winding, RF. So my current IA is in this direction, right? External supply is connected across the motor terminals. So my current will flow like this, okay? Suppose motor is running at some particular non-zero speed. So my back EMF will be non-zero, right? Now I am going to disconnect this supply and I am going to put a external resistor here. So what will happen here? This back EMF will act as a source and this will try to circulate current in this direction. But tell me, here when back EMF will act as a source, then my current direction IA will be getting reversed. If I consider this IA is a positive, then whatever the anti-clockwise current that will flow, that will be like your negative. But we know in case of DC series motor, the torque is proportional to armature current square, na? Right? So here torque is proportional to flux into armature current, and flux is proportional to again armature current, because armature current and field winding, armature winding and field winding are connected in series, right? So here what we are doing in the rheostatic braking of DC series motor, please be careful. Check here, my field winding current is from left to right, na? If this is my field winding, how the IA is flowing? IA is flowing from left to right, right? So here I am going to modify the connections of the field winding in such a way that even though when we put an external resistor here, then when this back EMF will act as a source, then my current will flow like this. Check here, EB, like this the current will flow, right? So tell me, through the armature winding my current is getting reversed, but what about the current direction through the field winding? Here also current direction is from left to right. In this case also current direction is from left to right only, right? So here field winding current we are keeping same. So if field winding current is same means my flux direction will remain same. But armature current direction is reversed. So due to that my torque is getting reversed. Torque is getting reversed. Are you getting the point, right? Next, plugging. Plugging, or it is also known as a reverse voltage braking. In plugging or reverse voltage braking, we are reversing the supply terminals to the motor, okay, right? In this method the terminals of the supply are reversed. As a result the generator torque also reverses, which reduces the normal rotation of the motor, and as a result the speed decreases. Yeah, during plugging external resistance is also introduced into the circuit to limit the current or the braking current, you can say. Yeah, so here it is a circuit diagram. Check, supply voltage is reversed. This circuit is only for braking, only for braking, right? Yeah. Motoring connection remains same as it is whatever we discussed earlier, okay? So for braking the supply voltage terminals are reversed. So now this will circulate current like this, this will also circulate current like this, na? So my current, armature current will be getting reversed. Similarly, this is a circuit diagram for plugging of a DC series motor. Next, regenerative braking. In regenerative braking, the power flow is from motor towards your supply. Power flow is from motor towards your supply. So particularly for regenerative braking, the motor back EMF should be greater than the supply voltage. This is the requirement, right? So some of the examination they ask the question, for regenerative braking, which of the following is the required condition? EB should be greater than your supply voltage. Then and only then your regenerative braking is possible. And how to increase the EB greater than supply voltage? So for that you need to rotate the motor by using the external means. You need to rotate the motor for the speed greater than the synchronous speed, right? Yeah. Regenerative braking takes place whenever the speed of the motor exceeds the synchronous speed. Yeah. The braking method is called regenerative braking because here the motor works as a generator and supply itself is given the power from the load. Supply is now power consuming, right? Motor to source, the power flow. Yeah, next, quadrants of operation of converters. So some theory questions they have asked based on the quadrants of operation of converters. Okay, right. These quadrants of operations are defined by considering the load on a converter as a DC motor or a motor load, RLE load. Okay, right. So in different converters like rectifier, right, we are having the different loads RL, RL with free link diode, right, RE and RLE. Particularly that RLE load is nothing but a motor load, right? RLE load means motor load. Okay, right. So single phase semi converter multiple times, okay, in Janko Transco as well as your Polytechnic examinations, Polytechnic lecture examination, they ask the questions, right? Single phase semi converter, three phase semi converter. This operates in both operates in first quadrant. Operates in only first quadrant, means these converters gives output voltage, output current only positive. Output voltage, output current only positive, operates in first quadrant, right? Check, you can check in semi converter your output voltage is proportional to 1 plus cos alpha na? So if my output is proportional to 1 plus cos alpha, even though if I vary the alpha from 0 degree to 180 degree, then also my V0 average will be only positive, right? And in converters you will get the current as only positive. So here positive voltage, positive current, so first quadrant operation. Next is single phase full converter. Three phase full converter. Three phase half wave rectifier. In all these three cases, your V0 average is proportional to cos alpha. Cos alpha. So if alpha is less than 90 degree, cos alpha positive, your output voltage is positive. If alpha is greater than 90 degree, cos alpha will be negative, V0 average will be negative, right? So these converters gives output as positive voltage as well as negative voltage, but output current is only positive. So these converters operates in first and fourth quadrant, right? These converters operates in first and fourth quadrants. First and fourth quadrant. Next, dual converter. Dual converter. You might have heard dual converter. Dual means two. In dual converter, two full converters connected in anti-parallel or back-to-back. Okay. Dual converters gives four quadrant operation. It gives four quadrant operation. So it operates in all four quadrants. Right, it operates in all four quadrants. Okay, right. So let us discuss some important questions. If a DC motor is disconnected from the source and armature circuit is short circuited through a suitable resistance, the process is regenerative braking, rheostatic braking, plugging, no braking is possible. Yes, can anyone? Very simple question. Here, what is the type of the braking, or whether the braking is possible or not, he is asking. Yes, you can post your answers in chat box. Yes. DC motor is disconnected from the source and armature circuit is short circuited through a suitable resistance. Suitable resistance means motor is disconnected from the supply and it is connected across a resistance na. So if it is connected across resistance, what is the type? It is a rheostatic braking, right? Rheostatic braking. Next, a separately excited DC motor fed from single phase full converter with a firing angle 60 degree runs at 1000 rpm. If motor is disconnected to if motor is connected to single phase semi converter with the same firing angle, single phase semi converter with the same firing angle of 60 degree, it would run at. So it is given that first of all motor is connected to single phase full converter and when firing angle is 60 degree, then motor was running at 1000 rpm. Now the full converter we are replacing with a semi converter, and for semi converter also we kept the same power same firing angle. Then what is the speed of the motor they are asking, right? First thing here, recall the block diagram of the electric drive system. In block diagram of electric drive system we have shown output of converter is given as an input to the motor, yes or no, right? Next, so my output of converter, that is V0 average, is nothing but input to motor, all right? Next thing is V0 average is equal to VA. But what is the VA? We know VA equal to EB plus IRA na? For DC motor, VA equal to EB plus IRA. Now tell me whether he has commented anything regarding the armature resistance. No, right? So simply neglect the armature resistance. If I neglect the armature resistance, then my IRA term will become 0, right? So therefore I can get V0 average is equal to EB. V0 average is equal to EB, right? V0 average is EB. Now we know this is a separately excited DC motor. In separately excited DC motor, flux is a constant. If flux is constant, what is EB? EB is proportional to only speed, na? EB is proportional to only speed, right? So first thing is for single phase full converter, when we use single phase full converter, right? What is the V0 average? Is equal to EB, which is equal to, for full converter, V0 average is 2 Vm by pi into cos alpha. You need to recall these expressions, single phase full converter, single phase semi converter, three phase full converter, three phase semi converter, okay? And single phase half wave, three phase half wave. These 6 expressions you need to recall. So it is 2 Vm by pi into cos alpha. Alpha he has given 60 degree na? So it is 2 Vm by pi into cos of 60 degree. So therefore I can write cos 60 is 0.5. 2 into 0.5 means 1. So it is equal to Vm by pi. So my V0 average, which is equal to EB for single phase full converter, is Vm by pi. Means across motor how much voltage we are getting? Vm by pi. Then for what speed my motor is running? My motor is running at 1000 rpm na? 1000 rpm. Next, for single phase semi converter, what is output expression? V0 average, which is again equal to EB, which is equal to Vm by pi into 1 plus cos alpha. 1 plus cos alpha. So therefore it is Vm by pi into 1 plus cos alpha is 60 degree na? Alpha is a 60 degree. Cos 60 is 0.5. So it is equal to 1.5 into Vm by pi. Now tell me, when input to motor, that is back EMF, is Vm by pi, then motor speed is 1000. If motor input, that is nothing but back EMF, is equal to 1.5 Vm by pi, then what is the speed of motor? So can I write here directly as EB is proportional to N, so I am writing it as Vm by pi upon 1.5 Vm by pi is equal to, when EB is Vm by pi, the speed of the motor is 1000. When EB is 1.5 into Vm by pi, then what is the speed of the motor? That we need to find. Simply take the cross multiplication, you will get the N, right? So my N value is 1500 RPM. Here armature winding resistance is not given, so simply you can neglect it. Simply you can neglect it. Okay, right? So if armature winding resistance is neglected, your output of converter is nothing but back EMF, right? So answer is 1500 RPM, option C. Next, yeah, in a 4-quadrant DC motor drive system controlled by two-phase controlled converters, controlled by two-phase controlled converters, phase controlled converters. The current and voltage of converter 1 operating in first and 4 quadrants. Converter 1 is operating in first and 4 quadrants respectively are, right? So it is like they have given single phase full converters, two full converters connected in anti-parallel like a dual converter, and converter 1 is operating in first and 4th quadrant. Then what is the direction of voltage and current he is asking. So first and 4th quadrant means, what is the voltage and current polarity, right? This is the first quadrant, this is second, this one is third, and here it is the 4th quadrant. So first and 4th means voltage is positive, current positive, yes or no? Voltage positive, current positive, and 4th quadrant means voltage negative, current positive, right? So voltage positive, current positive, and voltage negative, current positive. Option B is the correct option, right? Option B is the correct option. Next, in a 3-phase inverter fed induction motor drive, the total harmonic distortion is 4%. THD he has given, percent THD. We are having the concept of THD in inverter chapter, right? It is 4%. If the maximum value of fundamental component of load current is 4 ampere, right? So maximum value of fundamental component of load current, that is I01 max, is equal to 4 ampere. Then RMS value of net harmonic current, okay? Net harmonic current RMS he is asking. RMS value of net harmonic current. Right? Yeah. So what is the expression for THD? Percent THD is equal to under root I0 RMS square minus I01 RMS square upon I01 RMS into 100, right? So now from this percent THD is 4, which is equal to, first thing is what this numerator term indicates. The numerator term, check this carefully, under root I0 RMS square minus I01 RMS square means from total load current I am subtracting the fundamental component. If from the total load current fundamental component is subtracted, then whatever the remaining term is there, that term is nothing but your harmonic current. That is nothing but the harmonic current. Check, recall the inverter expression. We know in case of inverter, output voltage, output current consist of only odd harmonics, right? In that fundamental component is there, 3rd harmonic, 5th harmonic, 7th harmonic, etc. So addition of all these harmonics and fundamental component, that will form your total load current. So from total load current, if I subtract fundamental component, then I will get only net harmonic current. Net harmonic current. So therefore I can write net harmonic current upon I01 RMS. I01 max he has given 4 ampere. So RMS is 4 by root 2 into 100. So therefore from this you can write net harmonic current is equal to 0.04 into 4 upon root 2 na, right? So check the options. 0.04, yeah, he has given in terms of 0.08. So it is 0.08 into root 2, right? Yeah. 0.04 into 4 means 0.16 divided by root 2. 0.16 by root 2, you can write it as a 0.08 into root 2. Next, a separately excited DC motor is energized from 440 volt 50 hertz 3-phase full converter. Yes, 440 volt 50 hertz 3-phase full converter. The input voltage to the motor for a firing angle of 45 degree in volts is. Only input voltage to the motor they are asking. Input voltage to motor means output of your converter, right? So what is output voltage of converter? Input voltage to motor is equal to output of the converter. Yes, here we are having the 3-phase full converter. So expression is 3 VML upon pi into cos alpha. VML means peak value of line voltage. So it is 3 into 440 into root 2 upon pi into cos alpha. Alpha is 45 degree. Cos 45 is 1 by root 2 na. So here root 2 will get cancelled out. Yes, 3 by pi into 440. 3 by pi is like 3 upon 3.14 na. So it will be like 0.955. 0.955 into 440. That will be like 420 volt. 420 volt. So answer is option A, right? So friends, these are the some important concepts and questions related to the drive system. Okay, please try to solve the questions. Okay, right. So we are going to stop here. Thank you, thanks to all of you, and all the best for your examinations. Thank you.